Welcome to the Futurati podcast. Any member of the Futurati is somebody who believes in the power of the future. We know there's a better world ahead, and we indeed have the power to make it so. In our podcast, we talk to the best minds in the world about the most urgent problems facing mankind today, and we hope you learn as much from them as we do. I'm Thomas Fry, a professional futurist and keynote speaker.
And I'm Trent Fowler, a machine learning engineer and author. Thank you for joining us. Good evening, everyone, and thank you for listening to the Futurati podcast. Tonight, we're joined by Justin Ging. Justin is Chief Commercial Officer for Honeywell Quantum Solutions, where he leads the commercialization of next-generation quantum computing systems. Prior to joining Honeywell, Justin led marketing teams at Samsung Semiconductor and Micron Aptina and managed strategic projects at Analog Devices and Bell Labs. If you enjoy this interview, please don't forget to like the episode and subscribe on YouTube or wherever you get your podcasts. Justin, thanks so much for joining us on the show.
Glad to be here.
Why don't we start a little bit with your background and your interest and kind of what brought you to working on quantum computing?
Yeah, so I've always had an interest in being on transitional technologies, things that are world-changing, major technologies, and I've had the pleasure of being a part of many transitions through my career. Started in with more of an engineering background. I was double E and wanting to work in that space, and I landed at Bell Labs in optical fiber and photonic devices research, and what we were working on there was how to build the backbone of the internet. How do we make it higher capacity? And as we know, what has happened over the past 20 years with the internet, it's just an explosion of traffic, and
so that was you, huh? You're the one.
Well, it's there that I found my true calling is more on the marketing side. It was really about how to transition ideas out of the lab and into commercial technologies. And so chasing that dream, I applied that kind of thing to other technologies. And after business school, landed in image sensors, which was in camera phones. And we know how we transitioned from having just the tiniest little quarter VGA type image on our phone that was like a toy to, well, now you don't need a pocket camera at all. You carry your phone around. It's got high quality camera images. So, world changing as well.
Yeah. So how would you describe the state of quantum computing as it stands today? I tell people sometimes that it's kind of like the ENIAC computer stage of quantum computing. Other people, I say, well, we're in the stage where we're trying to decide between Betamax and VHS. There's
a little bit of both, probably. Yeah, I mean, I think that there's an archetype now. We've seen how classical computing can progress. We can refer to an ENIAC, so it's a different starting point. But yes, it's still early days. Yes, we still have a long way to go. I think we're going to see it go much, much faster than it took for classical computers because we have a model, we know where we're going, and we're very zeroed in on the types of problems. Maybe we don't know exactly what those killer apps are, but we know the kind of problems they are. And people are very closely looking at how they can apply quantum computing to those problems. And I think it'll make it move very quickly.
I tend to agree that it's going to be a lot quicker, but I think I have a slightly different reason for that. So I was wondering if you might elaborate on why you think this particular transition and this particular computing paradigm will evolve more quickly than the original computing paradigm did.
Well, I'd say part of it is due to the technology. So a lot of the pieces that came out in the early days of quantum were about who the players were out there doing certain types of technologies like superconducting or others. And based on what they were saying in terms of, well, here's how many qubits we need to make a logical qubit, or here's what we need to do. A lot of those things from years ago, which were based solely on their technology, were out there as like, oh, okay, that's common knowledge. That's how it is. Just same way that you say, well, if I search for what does a quantum computer look like, you'll probably see what their chandelier, the dilution refrigerator looks like, and they'll say, okay, that's a quantum computer. Turns out there are other ways to do a quantum computer. That's what we're doing at Honeywell. We're making trapped ion based, and it doesn't look like that. Looks much different. But that also translates to what does it take for us to reach logical qubit? What does it take for us to hit the fidelities that make a difference? It's different milestones that we need to reach. I think that's why it'll be sooner.
But I think that was also true in the early days of computing as well. You had vacuum tubes, and then you had transistors, and you had different plausible substrates for implementing the technology. So that by itself, I don't think would be enough to suggest that quantum computing will evolve very quickly. Or am I missing something?
Well, I think it's how many qubits do you need to have to do something useful? Nobody actually still knows,
right.
But the number is shrinking. People are getting very clever with their algorithms. And also from the hardware side, we're getting very clever with offering tools that are quite unique to be able to do some very interesting things. We have done some work that we've talked about at conferences where you can simulate or recreate circuits that would have taken a lot more qubits and apply and achieve them with many fewer qubits with certain things that we have. So particularly that is our mid-circuit measurement and reuse. So we can actually use a qubit for one particular operation, reset it, and keep it going in the computation, the same circuit to reuse it. And that enables you to get creative with how you apply it. And thus, like for example, we did a Bernstein-Bezzerani algorithm that you would have needed 100 qubits. We used 2 to be able to do that same circuit. So that's an extreme example. The ratio doesn't always hold up like that, but it is a capability that starts to say, okay, I can actually do something much bigger than I would have, with what I've been told previously.
So my background was at IBM, and IBM got its start with the card machines that they were reading all the cards, and they were doing the census, and they kind of got their big start because of the U.S. government hiring them to help with the census. Is there a similar type thing that might kind of jumpstart quantum computing?
I think there are a number of possible things that could jumpstart, and it's really about companies who are getting involved now to say, well, take a look at my problem in particular. And there's a variety of problems. They all kind of fall into a few major buckets around optimization problems, chemical molecular simulation, and acceleration of machine learning. But within those bounds, there are a number of companies who are trying to apply quantum, and they are starting to show at small scale how this can be done. And those are known problems that then as the hardware increases, there's a known path to how that could make a difference.
Yeah, well, one thing that I would say in response to people who claim that quantum computing is in the stages of vacuum tube computers or the ENIAC or something like that is that it's evolving in a world that is already saturated with classical computing, which means there are these classical compute pipelines all over the place in all these industries, including the ones you mentioned, many of which are just shot through with computational bottlenecks, which are amenable to solution with a quantum computer. And so we actually had a guest who asked what the killer app for quantum computing would be, and Thomas just asked what will jumpstart it. I actually think lots of things could jumpstart it, because all you really need to get a multi-million-dollar or potentially $1 billion application out of it is to find some place in a pipeline where they're trying to simulate the behavior of a molecule, like the Hartree-Fock procedure, something like that, and just solve that one thing with quantum computing. And for some of these pharmaceutical companies, that could be worth, billions of dollars.
Absolutely, yeah. The speed up of operations, taking time out of processes because of that computation. It may be that it's along the lines of, hey, quantum is a coprocessor and you speed up certain tasks, very much so. It could be, hey, we can tackle problems that we just couldn't have tackled otherwise. And it could be very specific, focused problems. And, we see a vision where the hardware and software kind of co-develop, and, we might go from a CPU style to an ASIC style where, once we zeroed in on one particular problem, we can actually start designing the hardware around that particular problem. Say, well, these 20 qubits only ever interact with these 20. So we're going to, do the system differently so that you can parse the system and have those things executing very optimally to do that particular task of value.
That strikes me as another interesting kind of way that quantum computing is different from classical computing, is that the hardware and the software are developing in tandem. And I suppose in a limited way that was true for early compute. I don't know the history all that well, but I'm sure they were writing simple code. But I think what they're doing now with quantum computers, the software and the algorithms they're trying to run, are a lot more advanced than what the ENIAC equivalent would have been in the 40s or 50s. So are there any unique challenges or advantages that come from that fact that the substrate and the software are developing at the same time?
I think it ends up being a benefit, and both kind of inform the other. So I was mentioning about how some of the hardware features that we have enable options for the algorithm writers. Equally, algorithm writers when they know what the hardware is, can leverage that to get creative. There are certain pieces of software that people use for quantum right now that are not optimally designed to do some of the capabilities with looping and conditional branching and these kinds of things. And so, both sides need to make changes and adjustments. So I think it's a shared symbiotic relationship.
Do you need conditional branching for quantum computing? Isn't it if and else at the same time?
Up until we talked about our mid-circuit measurement and reuse, all quantum circuits, you do everything, and then at the end, measure everything out, and that's what you have. What we're able to do is take out a subset of qubits, one or more qubits, measure those without destroying the rest of the quantum information, find out 0 or 1, get some insight into what's going on, and take an action based on it. Put it back into the computation as something else, and now I know that maybe I want to go one way or the other based on whether that qubit was a 0 or a 1. That's conditional branching that didn't exist before that we introduced that feature. Now others are starting to follow us down this path because it's amazingly powerful, and particularly quantum error correction is one of the key things that just requires this kind of capability.
Can we talk a little bit about the resampling or reusing of the qubits if that's not proprietary? I've never heard of that before.
Sure.
It seems like that would be enormously powerful. How does that work?
So if you think about how our QCCD architecture for our trapped ions, it's like a railroad track essentially, and along that track we have electric fields that are creating essentially a bowl-shaped field that's holding the atoms inside that, the ions, and then we're using lasers to shine onto those ions and do the quantum operations. And we move our ions. This is different than other people that are doing trapped ion. We physically move ions away from each other and into different zones where we have the lasers aimed. So what we can do is take 2 qubits, move them relatively far away from the others, have a nice quiet interaction by themselves. That's how we keep our fidelity very high. You can have that gate zone, we do the gate operation, and then they're entangled or have that operation, and we can separate them again, move them, and interact them with any of the other qubits. So what that, number one, it's really about how we achieve our high fidelity. It's how we have our all-to-all connectivity. So any qubit can directly interact without having to pass its quantum information down a chain where you're kind of losing fidelity each time. So both of those are benefits. But this mid-circuit measurement means when you take one of those qubits away and you can read that out, you can check, is it a 0 or a 1? All the other qubits are far away. They're not collapsing their quantum information. And so now that you've read out that qubit, it's essentially ready to be reinitialized. So we can put it back into a known 0 state, send it back in as if it was a fresh qubit that hadn't done anything else. But you leave with the classical information. Was it a 0 or 1?
How is it that I'm still not clear on how that doesn't cause the collapse of all the rest of the interacting qubits as well? I mean, if they're entangled and they're involved, then how is it that you can measure this one without causing the collapse of the rest of the system into a classical?
It's not that they're completely unaffected, but they all still have their own entanglements that are related. So it's the ones associated with that particular qubit.
So why isn't it that you can just reuse 2 or 3 qubits to do any computation you want to? I mean, what is it that drives the diminishing returns of that?
I don't follow your question on that one.
Well, so if you're able to do a mid-circuit measurement and you're able to execute an algorithm that normally takes 100 qubits and you can do it with 2 qubits, why can't you just keep recycling the 2 qubits to simulate 1,000 qubits or 10,000 qubits or something like that?
Some algorithms you can. So it's the Bernstein-Vazirani that I mentioned. If you look at that circuit, that quantum circuit, it essentially looks like a parallel circuit. You've got all these qubits. But if you spread it out and you take a look, it's actually one of these qubits does an entangling, it does a measuring out, you get something from it. And for the rest of that circuit, that particular qubit's not doing anything. So what we can do is switch that around to a serial operation. So I have 1 qubit at the bottom and this one at the top is doing the entangling, doing the measure, read it out, reinitialize it, and do what the second qubit would have been doing in that parallel operation, and then do what the third one is, and then do what the fourth one is, and spread that out in kind of a linear path. So that would be my best description of it verbally, would be going from parallel to serial. And because we have long coherence times and high fidelities, we're able to achieve that.
Is the long coherence time a function of the fact that you're doing a trapped ion system? Is it just easier to
very
maintain
much
that?
so?
Okay.
Yeah. So our our coherence times are on the orders 3 to 6 second type range. So that doesn't sound like a lot, but when you compare that to something that's 3 orders of magnitude smaller than that, it's a big difference.
For sure.
Now, our whole system doesn't operate on the same speed. So somebody could say, oh yeah, but it's slow. It's relatively slower, but the ratio of how much time do you have to do things to how long does it take to do things, we can get more done in our total amount of coherent time by at least an order of magnitude, if not 2.
That's remarkable. So, I mean, this might be a silly question, but you're confident trapped ion systems will be the substrate for quantum computing going forward? Do you think you'll win out?
That is the technology that we chose. Will it be forever? Hard to say. I mean, technology changes over time. Different things come up, but from our vision over the next decade, we are confident in the technology that we've chosen.
So what is it that you do as the commercialization of quantum computing at this really early stage?
Well, one of the things was we need to make people aware of what it is that we have and what we're doing in order to be able to sell. Commercialization is about generating revenue from what we have. I think so. Just becoming aware of it, but also then forming the partnerships necessary. That we are very focused on producing the best hardware possible. But that's not the only thing you need to be successful in providing solutions to customers. So we've developed a number of partnerships globally, and building out those partnerships, and also just finding some of these applications. So digging deeper on how some of these things can be applied, and trying to develop those stories around what it is that quantum computing can do. And one of the challenges with commercializing is what quantum computers can do today is not the same as the vision that everybody wants from quantum computers. We're getting there. We're on a path to it. But what's available right now are systems that people are using not to provide those answers to those computational challenges, but rather right now it's a tool for learning and developing and starting to apply and starting to focus. So that is part of the challenge, is being able to communicate the what is here now versus what will be here in the future, and making that distinction.
Yeah, can you talk through a little bit about what a customer looks like today and how that will evolve over the next 10 years?
So enterprise customers today are really looking for building some of the fundamentals. So it's not that you're going to go and use quantum today to optimize your financial portfolio, but you are going to start doing some of the fundamental quantum algorithms that would be underlying that. So if you're looking at logistics and how to pack boxes, you're not looking at how do I pack my whole plane. You're looking at, can this work with a few, let's say I have a big box and 2 smalls. Does the quantum algorithm actually sort out and come to the right answer? We know that what the right answer is. So am I getting that with quantum? Is this a path? And then, as we add capabilities, which we are doing on a very rapid basis, can we check again and make sure that, if we add another box, it's still on a path? And what does that timeline look like? So there's a lot of learning coming out of it. That's what companies that are getting involved now are doing, is learning how to use quantum computers, whether it applies, what does the timing look like? Just knowing what the timing is a very valuable piece of business intelligence. Is quantum, am I on a path that 3 years from now I need to do something? Or is it a year from now? You were going to make strategically different choices as a company if you knew that answer.
What are some of the lessons that's coming out of that?
The companies are learning which things are applying. I think a large fraction of them are finding good fit with what they expected. They're seeing with our system that they're getting what they expected to get. So a lot of the early quantum computers, it was a mismatch of, is this just noise, or is my algorithm just not working? Where's the problem lie? With our users, they're seeing that they do a simulation, they run it on our system, and they see a very close match to that. And so they can be assured that their algorithm is going in a good direction and keep iterating that way.
So when you say they're running a simulation, are they running a simulation of a quantum system on a classical computer? So they're not actually writing algorithms for quantum hardware yet?
Oh, it's the same one. So you're going to take your quantum circuit that you've developed, you develop your algorithm, translates to a circuit. You'll run that circuit on a simulator backend, which is simulated with classical computing, and then you'll run it on actual hardware.
Oh,
and
I see. Okay.
you're going to hope that the answer is the same. With other systems, it's not always the case. With ours, it's usually the case.
Oh, very nice. What are some places where quantum algorithms are finding use that are perhaps surprising? So, I mean, everybody knows chemistry, everybody knows finance, logistics is kind of an obvious one as well. What are some places where you wouldn't have thought possibly that quantum computing would have a lot to offer, but in fact it might?
Yeah, it seems that among those few categories of the optimization, simulation, and acceleration of machine learning, that it touches almost every industry. So we continue to find new pockets of interest. Mining is one that was never really on my radar. It's kind of coming from tech fields, but it turns out that mining companies use optimization software on a daily basis to figure out where should I be mining, where are the best locations, which trucks should I send to where today, because I'm optimizing that against market conditions, which are constantly fluctuating. What minerals and high value metals are worth things.
Just to clarify, that's not Bitcoin mining, right?
No, that's real in the dirt, digging in the ground mining. Yeah.
Okay.
Transportation companies thinking about how do I best route things. And, you named some that just seem intuitive and obvious, but there's so many other possibilities. People looking at how do I best optimize where the satellites get their directions, or how do I best steer antennas for ground stations for communication. Just a variety of things, huge a number. And usually if you can name an industry, you can probably come up with some angle about how that's important. Another one that's come up recently is gaming. Can it work for better randomness in your game system? Can you have a less predictable as you're playing, that it's truly random, or can you use it for rendering or image analysis? There's all kinds of ways that people are looking at applying quantum.
So you say that quantum gambling might be a big thing in the future?
Can quantum help the gaming industry? So it turns out our quantum computer can do some of the highest quality random numbers that you can get. So you could argue where's the threshold of where it matters anymore, but yeah, there's levels they're extremely high randomness where you would say that might be very good for these gaming systems, like casino game.
Tell me a little bit about the image rendering. What is that like? How is quantum computing used for that?
Well, we're still looking into that, but some of the idea is around what's called inception rendering. So some of the work that's been done by some companies in quantum today have looked at some of the more basic types of things like handwritten numerals. Can you artificially generate data sets that can be used in these generative adversarial networks, so GAN networks with machine learning? So can quantum play a part in that? It looks like it can actually expedite some of those steps in the machine learning process and generate sets of data that help then train. And particularly this matters in fields where you don't necessarily have real data. There's not enough real world examples of it. If certain medical cases or things, that if it's a rare disease, there's just not a lot of evidence of that. And so, there's looking at how can I use AI or machine learning to accelerate that, and how can quantum be a part of that.
So in that process, is it mostly capturing, is it mostly trading on the fact that quantum is really good for generating randomness, or is it playing some other role in creating the data sets that go into the GANs?
Different aspects of it. In some cases, it's what you're saying is the randomness. In other cases, it's around being able to highlight where are the things that you should be looking at. So, of all the data that's out there, are there certain areas that those are the subset that I should be focused on, and kind of start to cull down the list so that classical computing can do what it's going to do.
That's remarkable. So let's talk a little bit about Honeywell specifically and what you guys are trying to accomplish. So what do you see as Honeywell's play in the quantum market?
So we are producing the very best hardware we can in order to accelerate that path to value. I think that's what everyone in the industry really wants, is what are those killer apps, and deliver those solutions. And our piece in that right now is to produce the very best hardware that we can. What that means is very highest fidelities, pushing the limits of both the number and the quality of qubits. We use the metric of quantum volume, which IBM had developed, and we think is quite good. There are other metrics, and we're looking at other ways to kind of show that performance. But right now, We think that's a good way to, in a simple way, characterize the capability of the system. So we're accelerating that capability and working with partners to kind of work on the application side of applying that. And we have a number of software partners who help in working with enterprise customers who don't necessarily have a staff of their own PhDs doing quantum research. And so there's a way to supplement that. The end customers bring in the application knowledge in all cases. They know their problems very well. They know how to apply classical to that. They know the challenges of it. And so they're bringing their piece. We're bringing the hardware piece. Our software partners are bringing that algorithmic expertise. And the three come together to work towards those solutions.
Yeah, so in the classic computer world, there's around 8,000 languages, a little over that. Do you see quantum languages springing up and going off on tangents like the traditional computing world?
It cut out for me. Sorry, can you repeat that?
Yeah, the classical computer world has a little over 8,000 languages. Do you see the quantum language volume growing? When I was at IBM, that used to be kind of the ways people could build a kingdom, is to create a language and then everybody would have to report to them to get answers, or how it worked.
So far, we've taken an agnostic view to everything above the stack where it comes into our system. So we leverage the OpenChasm interface language. So that is open source language that describes a quantum circuit. So it's essentially like your sheet music. And what that allows is, above that, users can work in whatever framework they want, whether that's IBM's Qiskit or Microsoft's Q#, Project Q, or a number of other software frameworks that are out there. They can choose to use that. That's like their composing software. But in the end, whatever software they're using takes that composition, puts it into, here's the music to play. And that's when it comes into our system to play that music. So to date, that's where we're focused, is really around taking that music and then playing it as best we can.
So you said earlier that Honeywell is trying to differentiate itself by manufacturing the best hardware that's available today. So can we just talk a little bit about what is involved in that? So you guys are trapped ion, maybe start there. I mean, presumably most of our audience doesn't know that from a superconducting qubit. So like what's a trapped ion? What are the advantages to that approach? And what are you guys doing to push the frontiers of what can be done with trapped ions?
Yes, so our trapped ion system is room size. So we're talking about multiple optics tables, about 20 feet long, 5 feet wide. Large part of that is lasers, bulk optics. We have several different frequencies of lasers. They all have to be finely prepared to be able to be shining on to the size of a single atom inside a vacuum chamber. So
it's portable then, huh?
It's
room size portable. Yeah.
Not meant to be portable. And there's some efforts in various places to, hey, how can we shrink this down? We think going bigger and being more precise is more important now. Maybe someday things start to get integrated. In fact, as we think about scaling, there's a point at which it's really difficult to shine a large number of lasers into a very small amount of space. And so over time, we will shrink that optics portion and start to integrate that into the vacuum chamber very close to where we're doing the ions. So thinking about waveguides and other types of technologies to do that. And there's a lot of precedence here in the telecom space where they use this with, waveguide technology and optical fiber and these kinds of things. That's all in the infrared. Because of the ions that we're using, or we're actually in the UV range. And so totally different materials challenge. And that's some of the work that we're already doing now for those next generation systems. So there will be a shrinking, but we're not small at all at this point. And so the focus then is on these atomic systems. We have ytterbium as our ion, and that is perfect by nature because all ytterbium ions or atoms are the same. And so we're starting with something perfect, and then there's noise in the environment from various sources. And we do our best to eliminate all those sources of noise and make it a pristine environment. So that's why we have a vacuum chamber. We empty that chamber as much as possible. It's less dense than outer space. We cool it down to help that vacuum. So we use liquid helium to get it to around 10 Kelvin, which compared to what the superconducting folks are doing, that's like room temperature compared to the surface of the sun. It's a completely different regime. And so we don't have those same extreme temperature challenges that they do. we could actually work at room temperature. The quantum part of it is not affected by the temperature, but by cooling it down, we take some of those distracting environmental concerns away. So if there's a stray gas atom in the chamber, and when it hits the wall, there's so little energy in there because the temperature is low that it'll actually stick to the wall. So it keeps it a very clean environment. We control magnetic field. We have very precise electric fields. Basically, anything that's going to create noise. Laser phase noise, we try to reduce all kinds of things that go into keeping it as noise-free as possible so that fidelity can be as great as it can. And we're, our spec, our worst fidelity is basically what you work with. So your limiting fidelity of all the things that affect it. Our 2-qubit gate is that limiting factor for us. And we're above 99.5% at this point. And we continue to push that higher. So
what does that mean exactly, qubit fidelity?
It means if you do 100 operations, or let's say 1,000 operations, 995 of them are coming out with the correct answer in a sense.
What would cause the other percentage point?
Well, any kinds of noise or imperfections in it where, quantum is a probabilistic thing. Right. So it's what percentage of things are coming out right. So you want that percentage of answers to be accurate.
How do you push the fidelity higher? Just make the environment cleaner?
In essence, yes. So there's a number of factors that go into what do we know of are causing these noise? What are these noise sources, and how do we go and tackle them? So it's like a Pareto chart that you would do in manufacturing. Like, this one's the worst offender right now, so I'm going to go tackle that one and see what I can do to reduce it, and then what's next on the list. And so it's kind of working your way down through those noise sources and imperfections and pushing it higher. And there will be some fundamental limit where it's just too difficult to get it perfect, in which case there will be a regime change to quantum error correction. So piecing together a number of physical qubits to make a logical qubit that has a much higher error rate, or I should say a lower error rate, higher fidelity.
Did I hear you say earlier that the system can actually operate at room temperature?
It can, theoretically, yes. I mean, the quantum, unlike superconducting, where you need that low temperature for the quantumness to happen, trapped ions can be done at room temperature. It's just that you then introduce a number of other sources of errors and problems and stability to the system, so it works much better for us to cool it down.
So that's very interesting. I would have thought the thermodynamic noise in the environment would cause it to collapse into the superposition to go away. So how is it that doesn't occur if you're using a trapped ion?
Well, we're storing our quantum information in the spin of electrons. And so, for example, moving an ion from one place to another translationally doesn't affect the spin of it. If your hair's blue when you walk down the street, it's still blue when you get to the other end of the street.
That's really interesting.
So what are the holy grails in the quantum computing world? What are the advancements that suddenly everything would change?
1 million qubits.
1 million qubits.
Well, we constantly get requests for very large numbers of logical qubits.
Right.
Because once you're in the logical qubit range, you're less worried about the error in the system, and now you can go and do a bunch of things. So we think a big transitional point will be logical qubits, and we've talked about some of our work there. We'll have some announcements near future as well about progress that we're making towards that. But it's this change in when things are noisy to when things start to get better. And even once you have a logical qubit, there's different error rates. It's not like it's not a binary, okay, now I have a logical qubit, I'm done. There is going to be a continuous improvement till we get to the kinds of error rates that you see in classical computers, where you're talking about 10 to the minus 15 or something crazy. It's a crazy number of nines of fidelity there. And eventually that's where it'll go. But there will be, we think, an important distinction between the pre-logical to post-logical. Now, you have one logical qubit. There's not so much you can do with that. There's a lot of experimentation, a lot of early R&D work. But as soon as you get 2 and 3, now you can start to get interesting. And when you have a number of logical qubits, that will be a game changer for some of these applications.
Does Honeywell offer its platform over the cloud? Is that something you guys have?
That's how we do it. Yep. So it's essentially a platform as a service. So people can access either directly through us or through some of the partnerships that we had. So one is we are on Microsoft's Azure Quantum service, so people can go there. That's transactionally the easiest way to get on our system. You can go there and sign up, and it's open for people to use. You make your payment there, and you get your access.
How many qubits are available for that?
So we have two systems. One is called the H0. That was our first system. That is 6 qubits. Our H1 system is currently 10 qubits, and it will continue to increase over the course of the year to more qubits. And then we will introduce another generation H2 next year, and that'll kind of pick up that number of qubits and also push on the fidelity.
Has anybody built anything just really amazing with that yet? I mean, are there any experiments that make you especially optimistic about the future of the technology?
There are some recent work that we'll put out some news stories on soon about some of the things that people have been doing. And there are some really interesting things in terms of, I'm trying to keep it out of the sensitive range, but related to manufacturing, how you would optimize in the manufacturing space, as well as some of the chemical types of simulation and some different ways of doing chemical simulation.
Yeah, one example that I came across that I seemed way out in left field was when you look at with Pixar doing Toy Story 1 and you compare it with Pixar doing Toy Story 4, the amount of information in every frame that they put together for the film is incredible. And so that's an interesting way of looking at how the escalating demand for computing power keeps ramping up, and so virtually every industry is facing that sort of same situation where the amount of information they're trying to work with continues to rise exponentially. So I can understand why you're saying that this is going to affect virtually every industry out there.
I think there's a lot of potential. Yeah.
Well, I was just going to say another thing is just the structure of the underlying problem. So you said that solving optimization problems impacts lots of other industries. And this is one of the things I've been trying to get at over time. And slowly a picture has kind of crystallized that there are certain kinds of problems that are just better solved with a quantum computer, and like optimization problems or anything involving differential equations or certain kinds of linear algebra optimization or linear algebra operations rather are especially soluble with quantum computers. And once you start to pull on that thread, you see it just applies so many different places.
Yeah, I think that's spot on. That it's always surprising when we hear new applications. Some things are very easy for people to understand, like truck routing. Like you have a service truck, he's got to make 10 stops. What's the best path or option to do? Or maybe you don't know in the morning. Maybe you set out and you go do the first one and then you re-optimize. And if you have capability to do things fast, there are other industries where they only do this optimization, once a day or once a month, because it's so costly computationally to get that answer that you kind of make do. But imagine just the fact of if you could do these things on a much more rapid basis, would you be more optimal if you could constantly be running this or be doing it many times a day? Those kinds of things could change. And even percentage point changes, single percentage point changes to some of these industries is huge amounts of money different.
Right.
So how much do you feel the kind of the competition in other countries breathing down your back? There's kind of a national pride at stake here, and there's a lot of other countries that are kind of chomping at the bit, working towards the same goals that you are. So does that come up on a regular basis for you?
Well, definitely quantum is a global operation. And I think, we see ourselves as a global participant in the ecosystem of quantum. There are a lot of countries that want to make sure that they're not left out, so that they have their own homegrown developments in quantum. They have their own quantum technology. I think there's room for everyone to be involved with it. So we don't particularly try to take sides or try to be exclusive in what we're doing. So, we form relationships around the world.
So taking a step back a little bit, I know that your background is in taking transitional technologies and bringing them to market. So I wonder if there are any general lessons you've learned in that process. So you're doing quantum computing now. You've done, really, really small sensing technology in the past. What are some of the challenges associated with that?
I think many times it comes out to being able to explain technology. Cutting edge technology is usually the hardest because people aren't familiar with it. It hasn't been out there. So being able to explain those technologies in ways that people can understand, and there's, that's how you present the data and how you show what you're offering and make the case for it. I think what we have found in particular at Honeywell is being true to what we're doing. So a lot of people like to talk about, oh, that's just marketing hype. We like to have data. And so we show, like we say, hey, we've achieved something. We try to put the chart in there. We try to show, here's what we've measured. Here's how it is. And be upfront with not making wild claims that are unsubstantiated. So being truthful to that. And sometimes that means we're not as far as it, some folks will get out there and say, hey, we're already there. And that doesn't really help anybody in the end, because then they'll perpetually be disappointed. We're like, oh, I thought we were there, but we're not. So we think just being kind of grounded in data and truth, but also being visionary to here's what the potential is, and inviting more and more people to get involved with it. I think with these sort of nascent things, it's about getting the involvement and capturing the imaginations of people, and having that ecosystem grow.
So a lot of it boils down to just telling compelling data-driven stories.
That's a good summary. Yeah, I think that's a big part of it for sure.
And I think that the inclusiveness and sort of openness of quantum computing distinguishes it from earlier transitional technologies, because right from the beginning, a lot of projects were open source so that anybody could fork the code and play around with it. And a lot of companies like Amazon or Honeywell or Microsoft are making it available over the cloud so that basically anybody can access it and start messing around with simple quantum circuits to try to build toy projects. And so do you think that is going to be especially helpful in the development of the technology? Like why is now the time to start doing that?
There's a huge need for more talent in quantum. There's very few. I think there's just starting now to be some degree programs that actually focus on quantum. And what that means, the focus is actually getting a sampling across a wider range of talents. So, quantum developers are often a little bit of physics, math, computer science, maybe one of the applications related to how you're going to apply quantum. Very cross-disciplinary, and there's a need for more people. The experts in quantum are there's not very many across the globe. And so I think getting that involvement and getting people trained on quantum, it's a different mindset about how you program a quantum computer. And we need to get more people involved. So from our view, the more people using quantum, thinking about quantum, developing their skills in quantum, it's all useful to help move the industry along.
So do we ever get to a point where or quantum computer replaces traditional computing?
Oh, so we don't see it that way. It's a little bit more like there are certain kinds of problems that quantum will enable, whether that be through an acceleration or whether it be through, I never would have tackled this kind of problem except that now I have a quantum computer to go do that. So between that, we see a big space for quantum, but it's more like it lives in harmony with classical computing. There are certain things that classical computers do very well, and so it's not a replacement activity; it's a supplementing.
So then it's like the smartphone of the future. You have that quantum chip inside, so you do your quantum calculations on one side, and then you turn the phone over to do the other calculations.
Maybe, or I think HPC is maybe, or supercompute centers are. You don't use a supercomputer for, checking your email, right? But they have a place in the computational landscape that certain kinds of problems are best done on a supercomputer. I think it's more like that kind of model.
Yeah, the one analogy that keeps coming up in my mind is that when maglev trains were trying to get off the ground, well, literally, I guess, but they were competing against traditional railroad technology, which had been improving again and again over the years, and so maglev trains really haven't reached their full potential. Is that a good analogy in a situation like this or not?
Yeah, I guess in a sense, is this a technology S-curve where this becomes a disruptor? I think it's not in the hardware itself necessarily, but it's disruptive in the types of computation that you can do. So what's done now is often shortcuts, like, hey, that's too hard, so I'm going to make an assumption here, which is not exactly right, but maybe gets me kind of close. That's what's done with classical computers. You run into something where you just hit a hard wall and you just can't do it a certain way. Quantum computers will open up some capabilities in that regard. There'll be certain walls that we can break through and do it differently and tackle some of these problems. And so from a capability point of view, I think there's an S-curve here. But from the actual hardware, it's not that quantum's displacing it. It's supplementing, like I said.
I actually think that's worth underlining because I didn't realize until I started doing research into quantum computing how common it is to have some computationally intensive process you're trying to run and then scaling it by bringing in all these really crude heuristics. It's like, well, we're just going to round all these numbers down and we're going to sample randomly throughout the search space or whatever. And that's the only way they can get it to work at all with a classical computer. And some of these computations, like if you're running Monte Carlo simulations for pricing action in a financial firm, it can take a month. They can run a month solid and then they get something out at the end, which is useful enough to justify the computation. But
it's usually 42.
well, I hope it doesn't always output 42 because I feel like you could save your AWS bill. But once quantum computing comes on the scene and is actually usable by a lot of these firms, they can just do the calculation outright, and they can just know what the molecule does over time and how its energy landscape evolves, or they can just know what the optimal risk allocation is for a given portfolio and set of assets, something like that. And you won't have to scale it up with these heuristics. And that will enable all sorts of strategies, like in finance, for example, that are simply impossible today. And so I think the potential, nobody's underestimating it, but I think the way they arrive at their estimations isn't quite right. They're not looking at it in enough detail to see where it will be applicable.
It cut out on me. Sorry, I missed your question portion there.
Oh, no, I didn't have a question. I was just making a comment.
Oh, sorry.
Thoughts?
It went silent for a couple of seconds. Sorry. I mean, just coming back to it, though, I think that it's about that creativity. And that is why companies are getting involved, because they're thinking through those kinds of things. How could this change my processes? When do I need to plan for quantum to be disruptive? How can I incorporate that into the way I do things now? And often it's companies who, a lot of people that we interact with and kind of the first meetup with a company is groups that they're charged with looking a few years out and which are these disruptors. So it's often people who are also looking at AI and blockchain and some of these other technologies and looking at quantum among those to say, yeah, we believe this is going to disrupt this. So we're trying to learn more about it. And that'll be the first contact. And from there, it'll spawn other types of interactions to get deeper and start to look at, okay, how do we do a proof of concept project in quantum? And then diving in from there and like, okay, how can we build our own team that's actually going to be developing this? And there's a progression that happens with companies as they get more and more involved.
Can you talk about the size of the quantum effort inside of Honeywell, or is that top secret right now?
So we have more than 130 people that are focused on our quantum. A large part of that is scientists and engineers who are building our systems. And we intend to continue to grow at a very fast pace as our systems get more capable, as we start finding some of these applications and applying it. And I guess we're a breakthrough initiative for Honeywell. We have BTIs in Honeywell, and we are one in particular that has been nurtured and is frankly having good success so far. Fingers crossed that we keep going on this path. And I think Honeywell itself has other initiatives to do different things to advance their field. This one in particular is one that's in the computation field.
So if somebody came to you and just showed you that they got their certification in quantum computing through the IBM course, is that somebody you take a look at if they don't have any other background?
I think there are a growing number of roles that, early on it was just physicists, AMO physicists. They're the ones who are developing the core, but quickly moved to, we supplement those physicists with a team of engineers who are building out the system in a very robust enterprise grade way, and expand it out with more and more software to apply it. I think in the next field, we're looking much more in the application of quantum and how do we best impedance match our systems with those companies? How do we best explain to those companies how quantum can help their business, and vice versa? How can we learn from those companies how to best apply it? So that application space. And I think anyone who has gotten trained to some degree in quantum, whether that's IBM's program or others, I think brings some of that underlying knowledge to it. And I think there's lots of space for them to find a spot in the quantum. So as we grow, I'd say chances are, yes, we would look at that person and see if there's a good fit in a variety of ways. So my particular side is on the business team, where, yes, you have to know some of the quantum, but yes, you also have to know some of the marketing and things. So I think people who are training up in quantum are probably coming from some other background as well. And I think that's useful to bring to quantum. So people who understand the business can execute their role even better.
Back in 1997, IBM's Deep Blue team competed against Garry Kasparov and showed that somebody could finally beat a machine could finally beat a world chess champion. Do you have any plans for staging any big competition like this to show that we've arrived?
It's an interesting concept. I have not heard of any grand challenge yet like that, but I like the idea. I think what we've been thinking about was a quantum decathlon to test systems. So what is a set of benchmarks that we could run all the kind of major systems out there against to show what, in a fair way, some are better at some things and some are better at others. So let's get out there and see who's good at which events and how to best characterize systems. I think there's a hunger in the industry to be able to just put a single metric and just say it's a whatever, give it a score, and it's very easy to understand. But quantum systems are quite complex, and because of the variety of technologies, that's hard to do. And I think that's something that in the short run, it's not the grand challenge like you're talking about, but it's a good way to get a sense of how far has quantum progressed.
So we're not going to see a quantum bartender competing against a human bartender.
Maybe that's the way we can get interest.
That's the killer app. Yeah, that's the
do that.
Justin, you anticipated one of my questions. I was going to ask you about a person who's interested in getting into quantum computing and how they might approach that. I think you did a good job of answering that already. But I did want to ask what advice you might give to companies who are considering this. So what does that process look like when they say, maybe we're squarely in the target of an industry that's going to be disrupted by quantum computing? How would you advise them to go about trying to assess their position?
I think it's really about assessing the kinds of problems that they have to tackle. And if those are quantum amenable, it's about starting down a path of a proof of concept to understand what does their problem look like in the quantum domain. So there's a sort of a mapping that needs to take place. And through that mapping, you kind of convert to a quantum viewpoint, a quantum circuit. You run that circuit, you find out, you prove to yourself, yeah, this is something that can be a game changer. And then there's a scale up process. And that scaling up is not just of our side with the hardware, but also the application of it. There's getting processes ready. It's understanding, let's say we did have this on a quantum system. How would we integrate it into the way we do business today? And what does that timeline look like? So companies that are engaged start to develop out teams of people and start to gather their own talent and start training those talent. And I think it's kind of a process and it's a journey. And it's those companies who are taking that journey or getting involved now are the ones who are going to be prepared as the progress gets made with these systems.
How much interest does the U.S. government have in what you're doing? Because I know there's lots of military applications that are possible with something like this. So I didn't know if that's come up a lot just yet.
So I think that a lot of the government funding is kind of through some of the NSF type grants or DOE type grants, and that's going through universities often, and then through those grants, universities can have access. But I think there's lots of room for research in this, and there are company or groups like AFRL and ARL who are doing their own research, and other labs as well. So a lot of work at various national labs, and I think that's where government's getting involved at this stage.
So you are at Honeywell, one of the major players in quantum computing, and you've got rather a privileged position from which to watch the technology as it unfolds. What is it that makes you most excited over the next 5 or 10 years? What are you most excited to see quantum computing applied to?
It wouldn't bother me how it gets applied. What that killer app is, it's going to be game changing. And I think it's going to happen not just in one spot, but I think there's going to be a variety of ways that it changes things. And I think it's seeing those applications come to fruition. I think the biggest transitional concept for me is that we go from, hey, this was a proof of concept, to, hey, this was something that we actually want to implement in production that's producing real value for us. I think that would be a huge change, and that would be one of the most exciting things that could happen, is we make that transition to, yes, you saved me even 0.5% off of my supply chain costs. Just the tiniest little bit would be really rewarding to be able to say we've transitioned from a little bit more of the R&D to, yes, this is an actual value proposition. You can use quantum to save money, go faster, help the environment, to reduce carbon emissions, whatever it may be, whatever that value producing thing is, that you've done that using quantum.
Well, fantastic, Justin. Thanks so much for joining us today.
Yeah, appreciate the conversation. Really enjoyed it.
Thank you. Well, this is great. Thank you.